So what we're going to look at here is one particular idea that was put forward years ago by a guy by the name of Niels Bohr. He put forward this notion, this model of the atom, which explains a lot of what we observe in terms of the energy levels and so on that we talked about earlier. So that's what we'll be focusing on in this particular video right here, the Bohr atom. So in order for us to understand this particular model, we have to go to something that is observed when white light is split up into different colors, right? So as stated here, white light, if it's passed through a prism or another thing known as a diffracting grating, then you end up with what is called a continuous spectrum. And this is a model of that particular type of experiment where you have a white light source, and the source is allowed to shine its light onto this slit right here. A beam of light will pass through the slit and then pass through a prism. Now the prism is something made up of some transparent material like glass or plastic, and what happens is that the different colors that make up white light is split by the prism as it enters this side and then emerges from the other side, and then you see the different colors being shown here, and that is projected onto a screen, and therefore what you see resulting is called the continuous spectrum. All right, so the continuous spectrum is basically the a chart here which shows you the different colors of light that when combined together make up white light. It's just that this experiment basically separates the different colors of light and projects it onto a screen. All right, so that's a continuous spectrum where it's basically the same colors that you'll observe in the rainbow. I'm sorry. Basically, it's the same thing. The rainbow that you'll see outside after a thunderstorm or while rain is falling is due to white light from the sun being passed through the droplets of water, and the same thing happens. It splits up the white light into the different colors, as you can see here. All right, so it starts with red, and then it goes into orange, then yellow, then green, then blue, then indigo, violet. All right, so that's basically the continuous spectrum. Now it turns out that when you have certain elements that are exposed to either high temperature or voltages, they emit light, but not the same thing as the white light that you'll get from a lamp or a sun. And one can explain the reason why that happens based on the atomic structure as put forward by Bohr. So when this light is passed through a prism or diffracting grating, you end up with a different type of spectrum. It's not a continuous spectrum, it's called a line spectrum. So for example, here we have a hydrogen lamp. It contains hydrogen gas at a very low pressure, and you have two electrodes, one that's up here and another one that's down here that you cannot see, and it's connected to an external circuit. You flip the switch, and what happens is that you get this light that is produced, which when passes through the prism, you end up with not a continuous spectrum, but a line spectrum where you're going to see lines of different colors. I don't think you can see it very clearly here, but there is a red line here, and I think you have a blue line here, and I think this is indigo, if I'm not mistaken, right? So you have different colors of lines, right? And you have, within the spectrum, dark regions, right? So that's called a line spectrum, which is different from the continuous spectrum that we saw when we separate sunlight or white light. So that's basically what happens in the case of hydrogen. And if you try other elements, you'll see something similar. Now, for different elements, they will have different line spectra, but basically that's what you're going to see. You're going to see lines in the spectrum and large regions here, big gaps where it's just darkness. There's no light whatsoever. All right. So hydrogen is one example. You can also have a similar thing happen with neon. I'm quite sure you're probably familiar with neon lights that you'll see at stores and so on. It's basically the same thing that's occurring where it produces a line spectrum. Okay, now let's look at the line spectrum of hydrogen in more detail. So this is basically what you'll end up with, right? And it turns out that each line corresponds to the wavelength of energy emitted when the electron of a hydrogen atom, which has absorbed energy when the switch was flipped, then immediately the electron falls back to a lower energy level. All right. These are specific lines, and therefore, because their colors are specific, they correspond to particular specific wavelengths. All right. So another thing, which I think I made mention of briefly, is that each element has its own unique spectral emission lines. In other words, each element that is subject to this experiment will produce a line spectrum which is unique. And this is very important because this is how, for example, scientists determine that there are certain elements are present in the sun. They have their special instruments where they can look at the radiation coming from the sun and they can identify the line spectra of particular elements and therefore can tell that there are certain elements that exist in the sun, like iron, which exists as a gas up there in the sun. Okay, so Niels Bohr is a person who carried out research on the hydrogen atom with respect to the spectrum that it's produced, and he came up with his model of the Bohr atom. So according to Niels Bohr, the atom consists of a nucleus, and you have electrons that will circulate around the nucleus within specific orbits, right? So we have the first orbit here, which is closest to the nucleus, then the second orbit, and then the third orbit, and so on and so forth, right? And he used this model to explain the fact that when you have a hydrogen atom producing a line spectrum, it is as a result of electrons falling from a higher energy level to a lower energy level. And therefore, when that happens, the radiation that is produced is equal to the difference in the energy levels of the transition that the electron is undergoing, right? And the radiation, of course, will have a particular color of light because they have a particular wavelength associated with them. So just to illustrate using this diagram here, let's say you have an electron in the third orbital or orbit away from the sun. Then what will happen is that if the electron falls down to, okay, why is this not moving? If the electron falls down to, okay, this thing is, okay, right. If the electron falls from the third to the second energy level, then, or orbit, then what happens is that that corresponds to the production of a photon of light, which is red or pink in color, right? Okay, this thing is really not behaving itself for some reason. I don't know why. Okay, I'm sorry about that. So if the electron falls from the third to the first energy level, then that corresponds to a photon produced, which corresponds to a green colored light, and that is responsible for the green line in the spectrum. And we can explain the other colors similarly as a result of electron transitions. Of course, he delves into a lot of calculations using a particular equation, which I won't introduce here. But basically, that's the Bohr model of the atom. Key thing you need to remember here is that the light that is produced is not produced continuously. So you don't get a continuous spectrum. You get a line spectrum. And the light that is produced is emitted in discrete packets known as quanta. Another term that is used is photons, right? Where, as we said before, we're talking about radiation behaving like a stream of particles. Okay, so that's basically what the Bohr model says. Basically what the Bohr model is saying is that you have the orbits, the electrons exist within orbits, and the electrons move from a higher orbit to a lower orbit, then energy will be produced in the form of a photon. Here it says an electron can have one of several possible energies depending on the orbit, right? And it turns out that the energy increases as the orbit's distance away from the nucleus increases, all right? So this is the third orbit. The energy of the third orbit will be greater than the energy of the second orbit, which in turn will be greater than the energy of the first orbit, which is closest to the nucleus. Now, the thing about Bohr's calculations is that it works very well in terms of explaining what is observed experimentally as far as the spectrum of the hydrogen atom is concerned. Problem is that it didn't succeed for heavier atoms, so therefore more theoretical work was needed to be done in order to determine more accurately what the atomic structure of different atoms are, right? But we won't get into that here. Basically, I'm just going to go back to this diagram right here, which is as a result of the Bohr model, and basically it talks about the fact that you have different energy levels, n equal 1, n equal 2, n equal 3, n equal 4, n equal 5, and all the way up to infinity. And the nucleus, of course, is closest to the n equal 1 energy level, which corresponds to the orbits, all right? Okay, I'm going to stop here and look out for the next